All right, thanks very much for the introduction. So yeah, I'm going to talk about overfitting today. I think how it fits in with the broader theme of this workshop. It's really, I guess, about how intelligent systems, or learning systems maybe, can, in some sense, decide when to reject or accept noisy data, and how that, in some sense, messes up with their general ability to make predictions about the future. Okay, so I'd say that's kind of my take on how to connect these two topics. Let's try and get on to the next slide. So first, before I go anywhere, I just want to highlight my wonderful collaborators. So Erin and Kedar are two PhD students here at UCLA. They're just wrapping up. Kevin is an enthusiastic third or fourth year undergrad, actually looking to apply for a PhD right now. And then Guido and Deanna are both professors here at UCLA. So all of this work is as much theirs as it is mine, probably more theirs. So just want to make sure credit is given where credit is due. Outline for my talk. So I'm going to talk about a bit of a background first, because probably appreciate not everyone has maybe heard of these different types of overfitting, or maybe they studied overfitting maybe in some computer science or machine learning course 10 years ago, and they're kind of a bit fuzzy on it. So I'll try and go slow at the beginning, make sure everyone's with us. I'll then kind of present a very simple and flawed case study with which to mathematically and theoretically analyze different forms of overfitting and understand the different overfitting behaviors and see what kind of factors drive the different outcomes that we see. We'll then do a little bit of a technical deep dive into proving benign overfitting in a particular regime, which is maybe what I would consider more practical, and then kind of have a bit of time to discuss kind of summary and then some avenue for future work, because I think there's a lot of exciting future work to do in this space, personally. All right, so overfitting. So let's just put ourselves in a very, very simple, easy to understand setting, which you've probably all seen before. But let's suppose I'm trying to learn the identity function. Or I'm not trying to learn the identity function, but my actual thing I will be given is essentially a task where I'm given data drawn from the identity function, so these samples. But unfortunately, due to either some measurement noise or maybe the fact that there are some variables hidden from me that I can't have access to, there is a bit of noise in the output, right? So you see these little x's are bouncing around this blue identity line. And then I'm going to fit some models, right? I'm going to fit my predictor to this data and see what I get. And in the simplest case, maybe, or not the simplest, but a simple case, I use a degree 5 polynomial. And you see I manage to interpolate the points at least partially, and the kind of function I recover, or the predictor I learn, is pretty close to this kind of true function that's kind of underlying my data, or the true kind of structural signal in my data. Okay. Unfortunately, if I do the same thing but with a degree 20 polynomial, I get a complete mess. And so this thing completely nails its objective, right, which is to fit the training points, i.e. these crosses. It perfectly interpolates all of them, but it does horrendously outside that very restricted training set, right? It doesn't generalize at all. Okay? So this is an example of what I'd call catastrophic overfitting, where even a tiny amount of noise can lead to terrible, terrible, terrible performance outside the training set. Okay? So hopefully that's intuitive, and that might be a model or a kind of picture you've seen before and you may be familiar with. Let's consider now another task, so similar but with a different model. And here I'm going to learn a function which is now, it's a binary classification problem, so I'm just taking vectors in RD, I'm mapping them to -1 + 1. And I'm going to, once again, I love simple problems, so I'm going to consider just a very simple partition. The x coordinate is the only thing that matters for these points. If it's got a positive x coordinate, it's got a +1 label, and it's red. If it's got a negative x coordinate, then it's a -1 point, and it's blue. Okay, so very simple problem. And I've got some training sample endpoints, and I'm going to consider some parameterized function class, and in particular, I'm going to look at a single layer ReLU network. Okay, if you're not familiar with that, I'll explain it a little bit later on. But essentially, like a really, really basic, very, very simple neural network. Okay, and a little bit like the role of the degree for a polynomial, I'm going to increase the width and see what happens when I fit this data, okay, over time. And so I've increased the width from 10 to 1,000 neurons, and this is basically each time I increase the width, I'm essentially defining a much more expressive model class, potentially, right? And we can see that each time, despite the kind of growing complexity of our model, we're learning a pretty simple description of the data, or a pretty simple predictor, okay? So I can play the same game again as I did last time, and now introduce a little bit of noise. And the noise in this classification setting just means I'm going to flip some of the points, all right? So it's still very, very simple. All I'm doing is now you can see that there are some red points now on the left-hand side in the kind of blue part of the partition, as it were. And there are some, some red points in the blue side and some blue points in the red side now, right? So these are, in some sense, corruptions, right? Noise that's maybe introduced, as I said, from maybe some sampling error or by some kind of hidden variable I've not access to, which means that actually these ones are apparently flipped, okay? And now we do the same thing again, and the question is, how bad is our predictor going to get as we train our network, okay? So as we increase the width, and we train for 1,000 iterations each time, how kind of chaotic or kind of kind of nicely partitioning will the predictor function we learn be, okay? And we can see that it is bad, it gets worse, but it's not kind of catastrophic in the same sense that we saw for polynomial regression, okay? So clearly the kind of parameterization, the noise, all of these different factors lead to much more kind of, I guess, rich set of outcomes for overfitting behaviors, all right? So you can see this right-hand side definitely doesn't look like a perfect partition, but it's also not awful, right? It's still going to do probably an okay job, right? There seems to be some robustness to the noise in this particular problem that we've studied. And so the takeaway from that is that although it can be catastrophic, it isn't necessarily catastrophic, right? So noise in our data, even when we don't have explicit forms of regularization encouraging simple solutions, somehow there's maybe some form of implicit regularization going on that means we choose a pretty simple solution which still manages to fit the data, and that means we still, in some sense, generalize okay, all right? So these kind of observations probably, maybe they were known beforehand, but I guess they became a bit more famous through a set of papers. So this is actually a paper from 2021, or at least these graphs are taken from a paper in 2021. But I think there's a first work in about 2017. And the kind of experiment that these authors ran was the following. I think they took, I can't remember exactly which image data set it was, but they took an image data set. They then trained a bunch of different big networks, or in particular kind of image classification models on essentially the original underlying data set, and then kind of randomizations of this data set, okay? So for example, purple I think is random pixels. This means essentially they took a random permutation of each image's pixels. And so in some sense, maybe you once had a cat, but now your cat is just completely scrambled by some random permutation, and the labels are still the original. And then even you've also got red, for example, where I leave the images alone, but I randomize the labels I give it, right? So now I'm labeling some cats as cats, some as dogs, some as buses, some as cars, etc. Okay? And the observation they made was, first of all, well, yeah, our neural networks, these are very powerful function approximators. They can learn a very rich class of functions. So they can fit perfectly all the data. That's why we see after a certain number of thousand steps, the training loss go to 0. But even because of that, you'll see that on the right-hand side, the generalization error growth is not necessarily kind of a step change, a phase transition. There seems to be some kind of general gradual decay in the test performance with the level of randomness in the data, okay? So this is what maybe we'd call tempered overfitting, and that's in the case where we think of only a marginal to moderate increase in test error as we introduce noise into our training set, okay? So this kicked off a lot of kind of interest in the space, and people started coming up with different terms. And so maybe the one that we're most familiar with, maybe from textbooks, is this idea of like harmful or maybe more extreme catastrophic overfitting, where a small amount of noise leads to a very significant increase in the test risk. Tempered, where the excess risk grows somehow proportionally with the amount of noise. And benign, which says below a certain noise threshold, say if only like 10% of my points are corrupted, then we see marginal if 0 excess risk, okay? All right. And so one of the interesting things about this is these kind of phenomena are not really covered by the traditional theory approaches. So for things like uniform convergence arguments, these don't really apply here because implicitly we're growing D with N, all right? And so when you step back and you think about what's actually going on, we're not really considering in some sense one problem and growing the number of samples. We're considering a sequence of problems. And we're changing the dimension, right? That sequence is with the dimension of the input data. So we're changing, in some sense, the underlying distribution. And so we're not going to get all these nice kind of concentration of phenomena in the same way that we would in, say, like the classical setting, where you fix the distribution and just draw more and more points. Yes?
So D is the dimension, and N is the number of samples?
Yes. So D is the dimension of my input data. So I'm always thinking a very simple setup. I'm just drawing vectors in RD, and N is the number of samples I have in my training. Or the number of points in my training sample. Yeah. So I should have clarified that. Okay. So in terms of theoretical characterizations, there's quite a lot of empirical work. there's quite a lot of attempts or unsuccessful attempts to characterize it in very specific settings, I guess. I'm not expecting you to kind of take this all in. Really, it's just a kind of a dump to say, hey, there's quite a lot of work that people have been doing and a bit of a taste of the kinds of things people have looked at. So there's a lot of work on linear regression and connections with things like the NTK. And then from about 2022, there's also quite a lot of work looking at single layer networks and nonlinear, kind of benign overfitting in nonlinear models, okay? But there are significant data assumptions, and for example, I think in all of these, we're only training like the inner layer, right? But this kind of setting is quite challenging because you've got to deal with this kind of non-convex objective and the training dynamics in that setting. So it's quite difficult, because of that, people have to make pretty stringent assumptions on the data. So to kind of make that a little bit more, I guess, put some meat on that kind of statement, the data assumptions people typically make in these kind of nonlinear models and studies of benign overfitting are very, very simple, right? So we typically think of binary classification on cluster data. So for example, we might have two clusters, one for -1, one for +1, and these might be both Gaussian clusters, right? And they both have means, and these means we're going to say grow proportional to some parameter gamma, right? And so in some sense, what are we doing there? Why is that interesting? Whenever we're thinking about benign overfitting, we're kind of trading off, there are components of the data which are useful, they're kind of signal or regularity, and they are meaningful to the problem at hand. And there are other parts of the data which are in some sense noise or nuisance variables, okay? And these are in some sense the bits that are the kind of, so the mean of your Gaussian might indicate the signal, right? Because if you're in the same cluster, then hopefully all your points, at least with high probability, are going to have a positive correlation. That's your kind of, I guess, your structural regularity. And then the noise is coming from just the kind of particular noise component that you're adding onto that mean, all right? Okay, and so what does a kind of statement look like for benign overfitting? What does like a kind of a theorem look like? Well, you're going to need D, some input dimension, N, the number of points in the sample, K, the number of corruptions, or in some sense, some like level of noise control, and gamma, this kind of encodes the strength of the signal, okay? And then you're going to make some sense, like statement that's to the effect of if K of N and D of N scale appropriately, and gamma is also well behaved in some sense, then either training loss is going to go to 0, if I'm using something like gradient descent or some other algorithm. And ideally, if I have some new test points, y and x, right, these are a new test point pair, then I'm going to make sure that they are up there, the error that thing's less than 0, right, because it should be greater than 0 if I'm saying y and f of x are the same sign. This thing should be less than some epsilon, less than or equal to some epsilon. And k and d and n are going to scale with epsilon as well, right, just to be clear. But this is the kind of statement that you're kind of trying to make, all right? So prior work primarily focuses on the role of gamma. So it's talking about how much signal regularity does there have to be in the data itself to see benign versus non-benign overfitting. And also the other thing that prior work has required is that the dimension is polynomial or omega polynomial in n. So typically things like d is like omega n squared, something like this. And the insight to why you need this is that if I'm imagining I'm drawing high dimensional random vectors, then in that setting, I can prove that points are approximately orthogonal. And then the training dynamics kind of simplify, because the noise component of one training point isn't going to interact too much with the noise component of another data point, right? And the only way these 2 points are coupled, or these 2 points in my sample are coupled, are going to be through the kind of signal component, right, the regularity. I'm going to make this like a lot more concrete in a second, but just to give you a kind of high-level bit of context. And then, so the kind of goals that I'm going to talk about today are, can we derive benign overfitting results in a slightly more natural, realistic setting, so D is omega n, and what is the role of, in some sense, what I'd call the sampling ratio, n over D, in driving these different overfitting outcomes. And you can think about some different scenarios that may be interesting. So for example, if D is like log n, then you're in some sense talking about some consistent covering of your kind of, some consistent covering of your data maybe, whereas n being roughly equal to D is going to give you some other relationships maybe, particularly if you look at this noise matrix, which we'll get into in a little bit. And so really trying to understand like how this ratio drives maybe, benign versus harmful versus tempered overfitting, right? That's a kind of an interesting open question really. Okay, so now I'm going to give a description of the kind of data model. I'm going to go to the whiteboard just because I think if I write it out, it's probably going to go in a bit more than if I kind of just present you a big slide with lots of information. So, and I'm going to kind of also make a big disclaimer that This is a really simple model, okay? It's incredibly unrealistic, and is therefore does have, it's kind of limited in what it can tell us about benign overfitting or any form of overfitting in a kind of realistic setting. But I guess the idea is that if we can kind of properly understand this setting, this very simple kind of model, and maybe it will tell us some principles that we can extrapolate and use as analogs to drive hypotheses about how overfitting works in kind of general settings, all right? So the kind of picture I want you to have is maybe something to this effect. So I've got, maybe these are my x and y axes, and I'm just going to consider a single cluster, okay? So there's some vector v, or some direction v, and it's scaled by some, I'll try and make this a bit bigger, because otherwise you're not going to see anything, gamma v. And then maybe there's some kind of cluster of points here, okay? And most of them should be pluses, right? But maybe there are a couple of negative labels thrown in there, all right? So this is the kind of incredibly simple setting I'm going to consider, right? So I can model this as saying I've got endpoints, and I'm modeling them as xi, right, is equal to gamma v plus epsilon I. And here I'm assuming a little bigger. Okay, yes. I'll try. I'm notoriously bad. My students always complain that I do this, where I start writing smaller and smaller. So yes, thank you for highlighting this. So here I'm just saying v is just going to be some arbitrary unit vector. And then I'm going to assume gamma is just some positive scalar. And I'm going to assume epsilon I, these are going to be, for example, they're mutually IID. That says mutually if you can't read it, I'm sorry. And so there'll be something like, generally isotropic's going to be kind of the thing we'll need, but we could have, for example, them being Gaussian, okay? Although that's not really strictly necessary.
What does isotropic mean?
Just kind of spread out all in the same direction. Or if I look along any direction, I've kind of got equal density. It's a rough way of thinking about it. And like points everywhere equally. So this would be something like 1 over d id minus vv transpose. Oh, that's getting a bit squished. All right. Okay, so this is our general model. And then we're going to have some good set, okay, or some bad set, which I'm going to call B. And this is going to be some subset of n. I'm going to assume B, the cardinality of B is equal to some value k, which is, of course, less than n. And then I'm going to call G equal to everything in n that's not in B, okay? And then I'm going to say that I'm going to have some vector y, which are my labels, all right? So this is minus 1, 1, n. And I'm going to say yi is equal to 1, or plus 1, for I in G, and minus 1 for I in B, okay? So, this is honestly probably the simplest setup we could have. We essentially have just a single cluster of points. The label is just saying, is everything in cluster? And everything should be plus 1. But we've corrupted just a few points, so some of them are minus 1, okay? And the question now is I'm going to try and use some model to learn this, right? So I'm going to think about a ReLU network, so f of x w. And this is just going to be equal to j equals 1, 2m. It's going to be a shallow ReLU network. And I'm going to fix the output signs as plus or minus 1, depending on whether it's an even or odd index. So I'm just going to call that minus 1 to the j. And it's going to be sigma wj transpose x. Okay? And here I'm talking about sigma z. This is leaky ReLU. So this is alpha z. Sorry, this is max of alpha z and z, okay, for alpha in 0, 1, sorry, okay. So, leaky ReLU is just a bit like ReLU, but we have some, instead of being 0 for z less than 0, we are some alpha z, okay. So that's the kind of architecture. And so all I'm going to try and do is I'm going to basically learn some parameters wj that's going to allow me to fit my data and then see if this generalizes. Okay. So my loss for LW, I'm going to define as follows. This is going to be the sum I equals 1n times the loss for on each point, right? The individual loss. So this is just yi f of xi w. And here, Lz is the hinge loss. So this is 0 or 1 minus z, okay? Right, so hinge loss, what does this look like? It just looks like this, okay? So here's 1, here's L, and here's Z, all right? So hinge loss is pretty common, so people used to like it a lot for things like support vector machines. We're using it just because it gives us a really nice update rule, which we can link back to a really classic algorithm, all right? So the perceptron algorithm. Okay, so what does the update rule? I'm going to run gradient descent on this thing, okay? And I know it's not differentiable, right? But it's almost everywhere differentiable, so for all practical extensive purposes, I can still define an algorithm that's in some sense inspired by gradient descent, which is going to work fine. And so if I do that, I'm going to end up with the following update rule. This is going to equal wjt plus 1. It's going to be wjt plus eta. And then let me just check. I need to make sure I don't make a mistake here. Minus 1 to the j. So just the output weight. And it's going to be the sum of I in ft. I'll explain what ft is in a second. Yi xi sigma dot ijt, all right? And so here, ft is just equal to the set of points that haven't achieved zero loss yet, okay? So this is just equal to the I and n such that yi f of x I w t, this is less than 1. And sigma ij t is just defined as the derivative of leaky value evaluated on wjt transpose xi, okay? So this is nice, right? Because it's an alpha or 1, right? We don't know what, okay? All right, so this is our update rule. If we try and minimize this, so I'll just write min with gd, we get this update rule, okay? And the question you might have is, okay, under what conditions will this update rule terminate? And what is the kind of structure? What will the weights I get back from this update rule? Will they kind of help me find a good problem that generalizes, right? Will it fit? Okay, gotta have some finger strength. The question is, okay, if I run my network on this data, will it learn a classifier that puts everything in this cluster as +1? Will it learn a classifier that puts some of them as +1, others as -1? Okay, will it benignly overfit? Will it harmfully overfit? Will it not overfit? We don't know, right? Even in this very simple setup, we're not really sure, okay? Well, we kind of are sure, but right now you aren't sure because I haven't told you, I guess. So let's just look at what it looks like when we do some experiments, okay, first. So here is the graph. And has this gone over 1? Yeah, it's gone over 1. We see the following, okay? So this has, I'm varying d, so I'm varying my input dimension. I'm fixing n about 100. I'm keeping k as 10, so I've got a misclassification rate, or sorry, a kind of noise rate of about 10%. My network width is fixed about 50, so there's nothing kind of NTK-like happening here. It should be in the rich feature learning regime. My learning rate's 0.01, doesn't matter too much. And I'm training for a lot of epochs, like a lot of epochs, okay? 100,000, okay? And so we see something quite interesting. We see kind of on the left-hand side, maybe I can use this. Is this working? Maybe. Okay, over here, so for small d, or d much smaller than n, we're getting what looks like almost like no overfitting, okay? Because the training error is stuck at around 10%. And you investigate this, what's happening is none of the corrupt points are being fitted, but the test points are being, and only the clean points are being fitted. And the thing we're learning is, in fact, generalizing perfectly, right? So we've in some sense learned just a perfect linear classifier which puts everything, including this cluster over here, at +1, okay? Now, it's hard to tell whether this would happen if we could train indefinitely. So this might also be a kind of facet of early stopping, but at least what this kind of result's saying is that if we have a small enough step size and initialization, and we have d kind of quite a bit smaller than n, right? Then we see a kind of overstopping plus low n leads to kind of a no overfitting scenario, right? Despite the fact that our network could very easily, in some sense, in theory, approximate the function that we've given it, okay? So m could be very, very large. You can see this doesn't really matter too much what m is, but you'll see the same effect, okay, which is kind of interesting. Right? So even though the network could, in theory, fit all this noise, it doesn't, right? It, in fact, chooses something a lot simpler. As d gets a bit bigger, we see suddenly this transition, right? So suddenly we start fitting corrupt points, and instantly it kind of starts hurting us, right? So the training error goes down, the test error goes up, and suddenly we see this big spike. And that coincides with the test misclassification error hitting essentially roughly around, or going just above the kind of base rate of 10%, and the training error falling to 0, okay? This says misclassification rate, but these experiments are stopped when they hit 0 training loss or when they hit 100,000 epochs. And at this stage, we actually find zero hinge loss, okay? So on this side, we haven't actually hit, of course, still some more training could happen. But once we get over here, in fact, we can't really, nothing's going to change, right? Because we've hit 0 training loss. So here we see something interesting, where now we're in this kind of tempered regime, in some sense, because the misclassification rate's proportional to our underlying corruption rate, all right? And then as d gets bigger again, we see this kind of drop off, all right? So, you know, maybe we've spoken about this maybe in some talks, but we see a kind of sort of like a double descent style phenomenon covering here, where d roughly around n, we get a big peak, and afterwards it kind of decays away, okay? And we've got benign overfitting. I would describe benign overfitting somehow as pretty much everything on this side of things, okay? So in this regime, I'm calling it benign overfitting because we're essentially growing d, and our error rate's no longer, in some sense, entirely proportional to this misclassification rate. If we make d big enough, then we get essentially 0. We don't pay a penalty for having any noise in our system, okay? So this is what I'd call benign overfitting, right? And we have somehow, we have low or 0 train error, and our test error kind of sort of becomes decoupled from our error rate or corruption rate. We then have a kind of tempered overfitting stage in the middle, where our train and test error scale proportional to k. And then we have, over here, we have a kind of no overfitting, at least no overfitting with early stopping, all right? So this is already kind of interesting. It's showing the role of different dynamics in kind of driving these different overfitting outcomes, okay? So any questions on this before moving on? Yeah?
If I did I don't know, let's go crazy, 500,000 max efforts, would I get the same figure?
I don't know entirely. I'm still kind of running these. These experiments I produced last week. Or I produced with Kevin, I should say. Should definitely not take credit from him. I suspect if you ran for long enough, all of this stuff on the left-hand side would maybe turn into tempered overfitting, would be my guess.
So the right-hand side would probably be the same, but the left-hand side?
Yeah, I think if you train for long enough, the left-hand side probably looks like the tempered overfitting. I don't know. It would be pretty cool, yeah. So I definitely need to run those experiments, yeah. And I think what would be one thing that we're trying to do at the moment is trying to say, okay, even with early stopping, can you characterize some stopping time up to which you would see no overfitting, for example? Because practically, you could say, well, essentially, you get no overfitting unless you train for some ridiculous number of epochs. That's kind of interesting, I guess. So that's one set of questions. And the main thing I'm going to talk to you today, because I actually have some results on this, is on the kind of benign overfitting side of things. So I'm going to talk about characterizing this kind of region and what happens there.
Michael,
Yeah.
quick question. For the line like separating benign and temporal overfitting, did you draw the line based on the turning point on the training loss, not the test loss?
Honestly, it's kind of a slightly fuzzy area. All I'm trying to say here is that in some sense the loss or the test error really is become decoupled in some sense from this corruption rate. During this period, I can increase d and I can just drive this down a kind of arbitrarily small. Okay, so in some sense that's my less than or equal to epsilon. But you're right. Maybe you could define it in a different way, where you say you could think about it in the training error sense. It's a little bit of a fuzzy definition, to be honest. Yeah, or that I'm giving you right now. But yeah, I think your suggestion is very, very reasonable. So yeah, you're right that here I've kind of hit it basically where I hit zero training loss on the training set. Yeah. Questions? Any other questions? All good? How much time do I have left?
So you have 20 minutes, including questions.
Okay. Let's see how we go. I will try and... Okay. So, what, sorry? No, because people get bored, like, honestly. It's fine, yeah. So this is a kind of statement that you can make, or this is what a statement for benign overfitting might look like. And so essentially, I'm saying something like, under the setting given in assumption 2, this is basically a description of a data model that's very similar to this one. I think in this paper, we actually consider two balls that are diametrically opposite and have a -1 ball and a +1 ball, and some labels flipped in either one, but it doesn't really make too much difference. And this is just a simpler model, which is the one I'm going to show you. Then we have this A equals AGD. This is just saying I'm going to train my network with gradient descent. Eta is my step size. And eta is very, very small, so I don't want to hide anything from you. To make all of this theory work, we need eta to be very, very small, so proportional to like 1 over mn times the largest in magnitude norm of the input data. And then lambda is also some very, very small number, which basically controls the scale of the initialization of my weights. So basically I'm saying the norm of my weights is very close to 0 for these results to work at the moment. And then all I'm saying, if n is bigger than omega log 1 over delta, so delta is this, in some sense, confidence. D is omega n, and this is the thing that's a bit new compared to other results, because everyone else, including us before now, was looking at D equals omega n squared at least, or more. K is equal to, so upper bounded by some constant times alpha squared n, so we can think of K as just some fraction of n. And then gamma, this signal strength, has got to be, in this case, omega 1 over k. Then the following holds. Okay? So the first statement is just saying I hit 0 loss. All right? So this is a training result. This hasn't got anything to do with generalization. It just says I hit 0 training error. So this in itself is like a little bit interesting, because I'm training on I'm using gradient descent on some non-convex objective. It's not immediately clear that you can prove that you get 0 training loss. But in fact, there's a lovely connection here. It's very simple. You can basically connect this whole thing with the perceptron algorithm and the same argument you use for the perceptron algorithm. And you can kind of almost verbatim use the same style of argument to prove this also holds for leaky Rayleigh networks. So this is a really nice thing. We use this. I think it was also used in a paper by Rudskis and some other authors looking at SGD on linearly separable data. The second thing, the bit that then's maybe perhaps a little bit trickier, is that then we can also provide some kind of bound on the probability of failure, right, of misclassification on a test point. So here you can see we get some exponential to the negative c, which is just some constant, times alpha squared d over k. And this is saying, so for bigger d, when d versus k is very large, then we're going to be able to drive our training error really, really small. Okay? So this is the kind of statement we'll prove. I'm not going to go through exactly a proof of this exact statement. What I'm going to do is look at a linear model and try and show you how you kind of can prove essentially an analogous result in that setting, just to give you the kind of flavor for the ideas. So any questions on this before moving on? Is it kind of clear? All good? Okay. All right, so proof sketch for the linear case. And this is really easy. Honestly, there's nothing very complicated. So what am I going to assume? So the first thing we'll talk about is the data and the max margin, okay? Sorry, my writing is very spidery. So simplifying assumption for now is that just the epsilon I are, as I said, drawn from this particular distribution. Okay? And so they're basically Gaussians, but they're Gaussians that are orthogonal to V almost surely. Okay? Right, and that's just convenient from an algebra perspective. It's just me being lazy, okay? But it's not really necessary. So then what we want to consider is the noise matrix. So we're going to consider N, which is a random matrix in N by D. And we define N as just rows stacked of these noise vectors. So epsilon 1, epsilon 2, epsilon N. Okay? And then we get a lemma from Vashinen in his high-dimensional probability book. So I'll just put Vashinen HDP, which says the following. So if d is equal to omega n plus log 1 over delta, then there exist constants C1, C2, which are bigger than 0, such that, I'll just put it here, a little bit dark, but I hope you forgive me. Essentially, the probability, such that with probability 1 minus delta, we have C1 sigma n less than or equal to sigma 1 n less than or equal to C2. All right? So all this is saying is that if d is a bit bigger than n, then with high probability we're well conditioned, right? So the smallest and largest singular values are just both bounded by some constants, all right? Okay. So why is that nice? Well, it's nice because we can essentially now determine whether, in this situation, we're saying with high probability that data is linearly separable. Right? Right? We can basically say if we have Z is equal to the right pseudo-inverse of our noise matrix, Y, then NZ equals Y, all right? So this is basically a condition we can use to say, OK, is our data linearly separable or not? And that's going to help us connect back to these perceptron algorithm style ideas. Right? All right, so we can also define, I was literally just using the right pseudo-inverses of n. It wasn't a big, it's not a big, it's not too, I'm happy to chat afterwards if you got that, yeah. Okay, so then I'm going to talk about the norm linear separator, which I'm going to call W star. So I'm going to call W star is going to be equal to argmin. Why am I not taller? W and RD. W squared such that yi xi w is greater than or equal to 1 for all I n n. Okay, all right. So that's hopefully an object we're all fairly familiar with. I just want a linear separator that happens to have the smallest norm, okay? All right. And I know that with high probability, right, if these omega n plus 1 over delta, the right pseudo-inverse exists, and therefore there's going to be at least one linear separator, and therefore there has to be a min-norm linear separator, okay? Okay. And then for, now we can do a very simple little lemma for ourselves about this. And so if, again, d is equal to omega n plus log 1 over delta, then with probability at least 1 minus delta, W star is going to be less than some constant c times square root of gamma to the minus 1 plus k. All right? So how do we prove that? Again, I'm not going to use any fancy tools in any of this explanation. This is all like very nice, simple little bits of math. Let's define. So we basically just need to construct a linear separator, which we can characterize the norm of. And we know by definition that's going to upper bound this thing. All right? So I'm going to construct a linear separator and then use the norm of that linear separator that I've constructed to upper bound W star. All right? So how am I going to do that? I'm just going to say, let this thing be 0, 1, n. And let, sorry, say minus 1. Yeah, it doesn't matter. And let ui equal minus 1 for I in G, and be 0 for I in B, and be 0 for I in G, okay? So this is some vector just in. I've got awful handwriting. Is it legible? Are we following along so far?
I'm very close, but I don't know for the other side. Can you guys see it?
Can you guys see this roughly okay? All right, cool. So then I'm just going to consider, so with probability at least 1 minus delta, the right pseudo-inverse is going to exist, okay, of n. So I'm just going to say then, conditioning on that event, I'm going to define this vector z, and I'm just going to call this thing n plus u, okay? And this is nice because this implies nz equals u, of course, and also we know that z is orthogonal to v, all right, by construction, okay? And moreover, if we then analyze the norm of z, okay, we have this is equal to this, okay? Which of course we can just use some inequalities that we're all very familiar with, hopefully. This is just this. And then this is just, I'm running out of space, so I'm going to start going right. This is going to be u over the smallest singular value of this. And we know that this thing is just going to have a constant singular value from our statement before about the singular values of n. And so this thing is in fact just equal to the norm of this, which is just square root k by construction, right? Because there's just k of these things, there's only k elements in B, over some constant c, okay? All right. I think I'm out of whiteboards over here. Oh, no, I'm not. There's another one. Wow. Ooh.
Smaller singular values of n. You had the singular value in the denominator, right?
Yes.
But you had the n pseudo inverse?
Yes, but they're going to be related, right? If I just take the SVDs, yeah? Yeah?
So on the left of the inequality, you have the pseudo inverse in the numerator.
Yeah, if you just look at the what is it going to be, the largest singular value of S pseudo inverse, that's going to be the smallest singular value of n, right? If you just take the SVDs. 1 over that, right?
Well, 1 over that, yes.
Yeah.
But
Did I have 1 over n? I possibly made a typo, yeah. So it should be like 1 over, like, yeah, here. Oh my God. Here should be like this. Is that what you're saying?
yes.
Yes.
If you say it's the smallest. Right?
Yes, yeah, sigma n, sorry. I'm indexing sigma 1 the biggest, sigma n the sigma 1 the biggest, sigma n the smallest, yeah. Oh, this is very stiff, sorry. No, sorry, yeah, good typo spot. Okay, so now I'm going to construct this linear separator that I wanted. So this is just 1 over gamma v plus 2z, all right? And what's nice about this is by construction, z epsilon I, right, just because of the way I made z, all right? This is going to be equal to 1 or 0 here, and this is going to be if I is in B, or 0 if I is in G, okay? All right? Maybe I should have made U plus 1, but either way, it doesn't matter too much, okay? So let's just, yeah, maybe I should have made U a plus 1 instead of a minus 1 there. But anyway, if I then look at now the, on any I, so for any I and n, we're going to have W bar xi, right? This thing is going to be equal to yi, 1 plus 2 z epsilon I. So no, sorry, this should be a minus 1. Minus 1, what's correct? And then this, of course, is just equal to plus 1 for I and G, and minus 1 for I and B. Okay. All right, so I've done it. I've constructed a linear separator that gives me, of course, it linearly separates my data. Yeah. All right. And then, of course, I can now upper bound my min norm linear separator using this W tilde. And then this thing is just C square root 1 over gamma plus K, right? Just by construction, right? Because if I take the inner product with this to take the square root, that's what I'm That's what I'm going to get. Yeah. Okay. So I've managed to, in some sense, keep that in your head for a bit, but we'll probably come back to that in a minute. But we'll need that because essentially, we're going to use this property, which I'm going to call approximately min norm, or approximately margin maximizing. And I'm going to show that linear separators, which are approximately have this property, are essentially good at generalizing. All right?
You have 5 minutes.
Oh dear. Then we can kind of consider how we can skip some steps. So if we consider just a generic linear model, we're going to end up with something, instead of considering our ReLU network, we can just consider a predictor, which is like W transpose X. And then what we're going to do is decompose our W into some component in the V direction plus some component in the noise subspace. Okay. And what we can show is that with some X that's drawn from our model, right? So gamma V, 1 over D ID minus V transpose, then X transpose W is going to be normally distributed. It's going to be normally distributed according to gamma V, right? That's going to be the mean of it, plus, and of course this, right? So this ID minus VV transpose, okay? And so we can use Gaussian concentration to bound the probability. So W transpose X is less than or equal to 0. You can show that this, just using a pretty trivial bound on the tails of a Gaussian, is just minus A squared over Z squared, gamma squared, D over 2, all right? So far, I've really used no complicated tricks, like nothing harder than you'd probably find in like a second-year undergrad maths course, right? All right, so this is the interesting part that we've got to think about. And in some sense, we just need to characterize how, or lower bound this quantity, right? So this is A. This is in some sense the amount of signal that our linear separator has with the amount of noise that it has, okay? And really, this is the thing I'm going to call the signal-to-noise ratio. And if I can lower bound this thing, I can prove a generalization result, okay? So how do we do that? Given I have so little time, I'll probably just kind of sketch. If anyone's interested, I can try and talk to you about it afterwards. Essentially, I want to show that this A value, if it's too small, then the only way we could fit all the data is if the noise is large. But if the noise is large, then we're going to have a large norm in our separator overall, which would contradict the norm on our the bound on W. Okay, so basically it looks like something like this. So if our, say W is the thing our algorithm returns, if it's approximately margin maximizing, then it's going to be less than or equal to sum times W star. Okay. And then the argument I'm trying to very kind of high-level sketch is if A is too small, then Z has to be big to pick up the slack to make sure we fit all our points. But if that's too large, then we show that this condition is going to be contradicted, basically. And so that basically lower bounds A. So we get lower bound for A. We use an upper bound of Z, which we can just get from our upper bound that we derived earlier on W star. And that allows us to upper bounds this. And we get something like, at the end of it all, something like exp to the minus C D over K, right? This is the thing it comes out at if we have kind of K, D, and N following the kind of relationships I discussed or gave in the slide before. Sorry, that was really kind of lightning quick. I appreciate maybe that's a bit frustrating. If you have any questions, very happy to talk about it any time. I'll probably try and wrap up. So key takeaways, I guess, overfitting is pretty nuanced, and a low training loss is not necessarily a red flag. So particularly if there's strong regularity or structure in the data, right? That's something we've seen. The role of the sampling ratio, N over D, in driving different outcomes is quite important. So we've seen from those pictures, we get a host of different things depending on the size of D. And theoretically, we've showed that D equals omega n. In this regime, it is possible to show benign overfitting. Okay. And then I guess the kind of interesting questions, lots of interesting questions still to do, but in particular, what about large values of n over d? So for instance, one, it would be really nice to prove a no overfitting regime, at least with some early stopping. And then two, it would be great to characterize this tempered regime. We have some ideas, but this is pretty challenging, okay? And then beyond that, there's a host of other factors that we might want to look at and how they influence overfitting. So of course, structure of the data, okay? We're looking at a very, very simple model for our data. The role of the architecture and overparameterization in general. Sorry, not overparameterization, parameterization in general. So what if we had a deep network? What if we had a completely different architecture? What if we use different activation functions? All of these things. The algorithm used for training, right? I've only looked at GD. What about other algorithms? And then an interesting thing that springs to my mind is this comparison with grokking. So in grokking, we generally fit our training data, and then we suddenly generalize. Okay, so in some sense, we're fitting the noise in the data first, and then suddenly we find the signal or regularity. And here it seems like we're doing like almost the opposite way around, right? We often fit the structure, so the signal in the data first, and then later on we learn the noise. So I think those kind of stages of training and understanding how these benign overfitting versus grokking dynamics kind of interact would be really interesting. Sorry, that's everything. I think am I good for time?
You have some time for questions if you have more.
Yeah, questions. Yeah.